Hello everyone, I am Amit K. Jain, working as Assistant Professor in STM Institute of Technology, Ujre. Welcome to today's control system session in relation to Module 5, State Variable Analysis. In today's session, we will be learning about the topic State Model. So, regarding what is State Model, what is the general representation of State Model, what is State Variable and what is State, they have all been discussed in the previous two videos. So if you have any doubt, please refer the previous two videos in regards to what is a state, what is a state variable, what is a state model. Now we will continue with the problems. So now we will quickly go through the problem statement. If you recall, in the previous video we had seen how to develop a state model for a given differential equation, but now we have been given a transfer function. So represent the transfer function given below in a state model, and this is form 1. Y of s by u of s is equal to 24 divided by s cube plus 9s square plus 26s plus 24. It is called as form 1 because in the given transfer function in the numerator we have a constant. If you have a constant in the numerator, it is called as form 1. So here the solution is very simple. You need to convert the given transfer function into a differential equation. Once you convert it into a differential equation, then the procedure remains same as you would solve for a differential equation. So first you perform cross multiplication of the given transfer function. So you will get y of s into s cube plus 9s square plus 26s plus 24 will be equal to 24 into u of s. So now this is in S domain, we need to convert this into T domain. For that you apply Laplace transform. So upon application of Laplace transform, this s cube into y of s will become y triple dot of t, s square into y of s will become y double dot, then 9, s into y of s will become y dot of t, 26 is written as same, then 24, y of s will become y of t, 24 into u of s will become 24 into u of t. Now you can observe, just by cross multiplication and applying inverse Laplace transform, we have represented the given transfer function in form of a differential equation. So from now on the procedure is same. Again, this is the differential equation which we have obtained from the transfer function, and again the first step is same. You have to identify the number of state variables. Here y triple dot, right? So the highest order is 3, so you will have 3 state variables, and again the state variables are chosen as same: y of t, y dot of t, and y double dot of t. x1 of t is y of t, x2 of t is y dot of t, and x3 of t is y double dot of t. Now again we need to develop state model, for which we have to develop x dot of t and y of t. So we will develop x dot of t and y of t. So let us first find x dot of t. We already know that the state variables are x1 of t is equal to y of t, x2 of t is equal to y dot of t, and x3 of t is equal to y double dot of t. Let us first find x1 dot of t. We know that x1 of t is y of t. Differentiate this expression, you will get x1 dot of t as y of t. If you differentiate, you will get y dot of t. But what is y dot of t? It is x2 of t. So we have our first state equation. x1 dot of t is x2 of t. Next we will find x2 dot of t. For that we will consider our base expression x2 of t is y dot of t. If you differentiate this expression, you will get x2 dot of t is equal to y double dot of t. But what is y double dot of t? x3 of t. So you will have x2 dot of t is x3 dot of t if you refer equation C. Similarly we will find x3 dot of t. Again our base expression is x3 of t is equal to y double dot of t. If you differentiate this expression, you will get x3 dot of t is equal to, again differentiation of y double dot is y triple dot of t. Now we have to find what is y triple dot of t in form of state variable and input. For that again we will consider the differential equation which we obtained from the transfer function. So now again we want an expression for y triple dot of t, right? So take all these terms to the other side, you will arrive at an expression like this. Now represent this expression in form of state variable and input. Now here you see we have y triple dot of t, but what is y triple dot of t? x3 dot of t. What is y double dot of t? x3 of t. What is y dot of t? x2 of t. And what is y of t? x1 of t, and input we may write as it is. So when we substitute all this, we will get an expression like this. Now if we rearrange this so that we will get x1, x2 and x3, we will have an expression like x3 dot of t is equal to minus 24 into x1 of t minus 26 into x of t minus 9 into x3 of t plus 24 into u of t. Now here you can observe x3 dot of t, that is the state equation, is represented purely in the form of state variables x1, x2 and x3 and input. So now we will represent these equations in form of a state model. So again, x dot of t is nothing but x1 dot, x2 dot, x3 dot, and we have our A matrix and we have our x of t matrix. In the last problem itself we have discussed how to write A. In case you are still wondering, here A is associated with x of t. X of t is x1, x2 and x3. So the coefficient of x1, x2, x3 in the expression for x dot of t. So the first row is x1 dot of t, right? So in x1 dot of t, what are the coefficients of x1, x2 and x3? So in x1 dot, there is no x1 term, so the coefficient is 0. There is x2 term, but coefficient is 1, so you will write 1. And here there is no x3 term, so the coefficient is 0. Similarly, you can write for x2 dot and x3 dot. Then we have our B matrix, which is multiplied with u of t. Again, we have already discussed how to write B, but again, in case you are wondering how did we arrive at B, again you analyze B is associated with what here? U of t. So the coefficient of u of t in the expression for x dot of t. So again you can observe the first row corresponds to x1 dot, the second row is x2 dot and the third row is x3 dot. In x1 dot of t we have no input term, so we have written 0. In x2 dot of t expression we have no input term, so we have written 0. But in x3 dot of t expression we have input term and the coefficient is 24 and therefore we have written 24. Now let us develop output equation. Again we know that output equation is given as this. So we already know that the output equation is y of t is x1 of t. So which can also be written as like this. Now if we represent the expression 4 in form of the standard output representation, that is y of t is equal to c into x of t plus d into u of t, we will arrive at this output equation, that is y of t is equal to, this is c, and again x of t is x1 of t, x2 of t, x3 of t. Here again what is c? C is associated with x of t, that means coefficient of x1, x2, x3 in the expression for y of t. So here in y of t we have only x1 of t term, right? So we will have coefficient for only x1, that is 1, x2 is 0, x3 is 0. Here again d into u of t will become 0 because in the output equation there is no u of t term, so u of t is 0, 0 into d is 0. So if you represent both equations as 1, then that is called as state model. So again we know that state model is a combination of two equations, state equation and output equation. Here state equation is represented in the standard form, x dot of t is equal to a into x of t plus b into u of t. Similarly, output equation is represented in the standard form, y is equal to c into x of t. Here d into u of t is 0. Again, this is how we arrive at a state model for a given transfer function if there is a numerator, if there is a constant in the numerator. Again, as always, if you have any doubt, feel free to contact, and thank you for your